had very briefly begun, and we put down some rules in here. I'm going to jot them back in real quick because I guess I didn't save this from last time. We had, this one was addition of exponents, this one was subtraction of exponents, this one was multiplication of exponents, and then this one looked sort of like we distributed the exponent. And we talked about the fact that if we have a power of 0, then by definition we call that number to a power of 0 equals 1. Everybody remember that? Okay. What I'm going to do next is I want to actually talk about why in the world these properties work. Because if you can't remember whether you're supposed to multiply or divide, it would be unfortunate to just guess the wrong one because you're just remembering the list of rules. So there should be some way for you to look back and say, oh yeah, I remember it works because of this. And it's also a good thing because some of you are going to have those kids in your class who are going to ask you the big old question of what? What's their question going to be? Why? But why does that work? And it would be unfortunate if you looked at them and had to say, I don't know. So I want to show you how these work because they're not terribly difficult. All right, so you guys know that this is supposed to be addition of exponents because that's the property 1 we did. So what we're going to do is we're going to actually break it down to look at the individual ones and show why it's addition of exponents. So what does it mean to have a to the 3rd power? Yeah, a times a times a. So that's a to the 3rd power. And what does it mean to have a to the 4th power? Right. Okay, so this is a to the 3rd. This is a to the 4th. Count them up. How many do we have? There are 7 of them. So what should this be if I were to write it down in simplified form? A to the 7th. And you notice, how did I take 3 and 4 and get 7? Add them. That's why it works. It's as simple as that. Okay, let's do the same thing with division. So from the previous slide, you know this should be a subtraction argument. You guys already told me that a to the 4th is 4 a's multiplied together, and that a cubed is 3 a's multiplied together. So what do you do in a problem where you have division like this? Kristen's drawing pictures in the air. Yeah, so it's Bailey. You do this, right? You reduce. You reduce like factors because it's all multiplication. What do I end up with? A, what's the power on it? 1. We don't usually write it that way, but I'm writing it that way for the moment to draw your attention to the fact that the reason we got the 1 from that is because I had 4 and 3 originally. And how did 4 and 3 become 1? Subtract, right? 4 minus 3 is 1. Okay. Number 3, we were supposed to understand that this is multiplication. So again, let's look why. So this one looks kind of like the number 1 rule. We talked last time about the primary differences. There's not another a base. I've just got sort of these parentheses and this additional exponent on the outside of an exponent. So what I want you to recognize, we already did this a to the 3rd. This is a times a squared. And that's what a to the 3rd is. You guys already told me that. So what in the world does it mean to have something squared? Multiply it by itself. Exactly. So this is that. And there's almost a redundancy involved because by simply putting the a's next to each other, I mean multiplication, and by putting the parentheses in, I mean multiplication. So this is all multiplied, right? All right, so how many a's did I get? I don't think there's 9 of them.
Oh, 6.
6 of them, right. There are 6 a's here. So how do you take 3 and 2 and get 6? Multiply. Multiply to get that to be 6. And then the last one we had looked like this, where it looked like you're distributing an exponent. All right, so using what you told me to do on problem number 3, this has AB raised to the 4th power, right? So if squaring means to multiply it by itself, what does raising it to a 4th power mean? Multiply by itself 4 times. So this is AB, 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 and AB. Now, Carrie, this almost looks like the one you asked, doesn't it? I've got some parentheses around some components, and we understand that with the properties of commutative and associative, I'm allowed to distribute things around, not distribute, but move things around. Commutative allows me to move the numbers, which are my A and my B, and then associative allows me to regroup the parentheses. So if I use commutative and associative enough, I can understand that I can put all my A's together and all my B's together. Whoops, one more of those. So how many A's do I have? And how many B's do I have? 4. So in a very real way, it does look like I distributed my exponents, doesn't it? But again, let me remind you, that's because this was multiplication of the A to the B. If this had been addition of the A to the B, this would not have worked. Okay? Because we have to do that distributive property like you asked about Angela multiple times. So. Any questions on those? So let me clarify something that sometimes happens on your homework. I do not expect you to write out A when it says A to the fifth or whatever. But that's not my expectation. The only reason I'm showing you these last 2 slides is because I think you should know where they came from. I don't think you should be left wondering, was this the addition or was this the multiplication step? You shouldn't have to think through it that way because you have tools that allow you to make those decisions. Okay? So what you're using as you're using these rules is you're just using the rules. So if you end up with a question that asks you to do something like this, I do not expect you to write out a bunch of A's. I expect you to use these properties. Okay? So just for the sake of completing what I started, how would you start this problem? You don't need to write it 3 times. Don't need to multiply either.
Sorry.
Okay, so we're going to start inside the parentheses, right? And we're going to combine this A to the 5th and this A to the 4th, and it gives me A to the 9th. And then what am I going to do? Multiply the exponents, which is rule number 3, or property number 3, which is going to give me A to the 27. So we don't need to write anything out multiple times. Does that make sense? I want you to understand the purpose behind me showing you this. It's not to make your life more complicated so you can do more problems and more work and it's longer. That would be really silly. But you do need to understand where the things came from. All right, let's take a look at a couple of them here and how we would write these out. So very similar to the last one I just gave you, except that these have some numbers involved. So on the first one, you notice all of the bases are the same. 5, 5, and 5. So we can work through part A just like I did on the previous slide of that red one at the bottom. All right, so you notice we've got A to the 10th, A, 5 to the 10th, 5 squared, and 5 to the 4th. What do we have to do? Just add the exponents. They're added. Why are they added? Because I have the bases raised to powers, right? I have the same base power. This is property number 1. Okay. So I add my exponents. So this is 10 plus 2 plus 4 for a total of 16. B is different. What's wrong with B, or what's different about B? Bases are not the same, are they? And there's a couple of things you could do. There's 2 distinctly different ways to approach this. So somebody give me a suggestion of what you think you would try to do if you were working with this problem. Okay, that is one of the 2 distinctive ways to do this. So Kinsey says she would change the 6 to be 2 times 3. So this is 2 times 3 to the 4th power, right? And I still have a 2 to the 3rd and a 3 to the 3rd going on. Now what? Right, this is property number 4, right? That allows me to do a distribution of these exponents. So I can write 2 to the 4th, I can write 3 to the 4th, and I have 2 cubed and 3 cubed. You can combine the ones that have the same bases. So these 2 are both base 2, right? So I'm really using a commutative property when I do this. I'm reorganizing my numbers. It's all multiplication, and commutative is a property of multiplication. So we can do that. So I can regroup this so that I have 2's together. So I'd have 2 to what power? 7th. And if I regroup the other piece then together, I would also have a 3 to the 7th. Does that make sense? Okay. Next thing we're going to get into is the different properties of multiplication outside of exponentials. Okay, so these are the ones where we're just multiplying values together. They don't have anything about bases or products or powers going on. All right, so taking a look, there are 3 multiplication properties, or algorithms, excuse me. The first one is 48 times 32, and this comes from the expanded notation. So we're going to think of 48 in its expanded form. Do you remember how to write expanded form for 48? 40 plus 8, right. And then we're going to do the same thing with 32. We're going to write 32 as 30 plus 2. Now there's, this one will lead into the next one with a more visual picture of what's going on. But you actually saw an application of this in your homework last night. So if I'm wanting to multiply 48 times 32, this is equivalent to multiplying 40 plus 8 times 30 plus 2. Because 48 is 40 plus 8, 32 is 30 plus 2. So far so good? Okay. So the next thing you could actually do is you could do something that you guys learned in algebra called FOIL. Right? And it's just a glorified distribution is all it is. You're just multiplying every piece by itself, or by every other piece rather. So you multiply the 40 times the 30, and what do you get? 1200. And then the outer terms, you'd multiply the 40 times the 2, and you'd get 80. Your inner terms, you'd multiply 8 times 30, and you'd get 240. And then the last terms, you'd multiply 8 times 2, and you'd get 16. And then the result is simply a list of values you can add together. Okay? So you add it together, left to right, right to left, up, down, all the properties, all the different algorithms from section 3.2. We can combine them, and what do we get for our total? Surely somebody's already done it for me. Okay, do I have a second? Yes, excellent. Okay, so 1,536. So this feels kind of like algebra, but it's with numbers, which makes it a little bit less abstract for kids, because you're not dealing with A's and B's and things like that. Okay. I want to show you the next one, which is a visual way to do this now. Okay, so we're still going to think of the 48 as 40 plus 8. Maybe I shouldn't write it like that. I don't want you to think of it as factors. And we're going to think of the 32 as 30 plus 2. Okay? But what we're going to do is, this one you have on the board right here, Angela, over here, we're going to do it with picture. The picture doesn't have to be drawn to scale or anything like that. What you're going to do is you're going to draw a square or rectangle. And you're going to split it into fourths. And in each, along the top and along the left-hand side, you're going to write the individual values that you got from splitting up 48 and 32.
Would it matter which side?
Doesn't matter in the slightest. Yep. So you can put the 32 along the top or the 30 and the 2 along the left-hand side either way. And then each of the boxes is their product. Okay, the length and the width of a rectangle. So if you do 40 times 30, that's the 12, and then zeros, 2 zeros. You do 30 times 8, that's your 240. You do 2 times 40, and that's your 80. And you do 2 times 8, and that's your 16. It's the same 4 numbers as the previous slide, right? But it's got this nice visual to sort of describe where it's coming from instead of this algebraic approach. And that visual is really appealing to some students. It's great. You've got a reason for why in the world this works. You got a visual. The other thing that's really nice about doing this is notice all of the multiplication was a single digit times a single digit. I mean, really. When you multiplied 40 times 30 on this slide and the last slide, all you really did was multiply 4 times 3, right? And then you included the 2 zeros. So you're really breaking this down into single digit multiplication, and that's nice too. So So your answer still, again, is the sum of all these guys. You can write them in whatever order you'd like. And you still get the same 1536, of course. So one more method of multiplication. And I will say that this is actually the method that I have taught my daughter, and the one that she resonated with for whatever reason the most. Okay, it's called lattice multiplication. Sometimes I teach it in contemporary math, so this would be kind of contemporary math. You may have seen this in there. Here's the way it goes. You take, I guess I could have done that, it's fine. You take a box just like you had the box before, and you split it into fourths. And the reason you're splitting it into fourths is for the same reason as the slide before. You have two two-digit numbers. If you had if you had two three-digit numbers, you'd split it into ninths, because you have 3 along the top and 3 along the side. Okay? So it's based on how many numbers you have. Because what you're going to do now is, instead of writing it as 40 and 8, you're going to write a 4 and an 8. And instead of writing things along the left-hand side, you're now going to write on the right-hand side the 3 and the 2. And again, it doesn't matter where the 4 and the 8 go on top or on the right. They can be interchanged. It would be fine. It does matter that the 4 comes before the 8, because that means 48, whereas if we switch to 84, that wouldn't work. Okay, so that part matters. The next thing you do with lattice, just like we did with lattice addition, is we split the boxes diagonally. Now, so you remember when we did lattice addition, what did we do next after we split the box? We did addition, yeah. What did we do when we did addition with lattice?
Add the 2 and then put the tens in the top.
Right. So we did some addition because we were doing addition. And then the tens value went on the top of the diagonal and the ones value went on the bottom of the diagonal. We're doing the same thing here, except that we're doing multiplication. So each step's multiplied. So again, the nice thing here is it's one-digit multiplication. The other nice thing here is that it doesn't matter what order you do anything in, because the box splits everything up into a two-digit number. So I can start in the top left-hand corner, I can start in the bottom right-hand corner, or anywhere else. So I'm going to just start in the top left. What's 4 times 3? 12. So I put the 1 on the top and the 2 on the bottom. That's the number 12. I do 8 times 3 and I get 24. 2 on the top, 4 on the bottom. 4 times 2 gives me 8, so I only have to put the 8 on the bottom. And then 8 times 2 gives me 16. 1 on the top, 6 on the bottom. And then it becomes like the lattice addition did. I split things along diagonals. So I've got this diagonal, and this diagonal. So I'm starting now at the bottom right-hand corner, and I have the number 6, and I write it down. Okay, so these numbers along the side, the 4, 8, 3, 2, they're not adding anything, I'm not doing anything with them, okay? I'm just looking at the numbers inside of my lattice. I move up to the next diagonal, I have 8 plus 1 plus 4, which adds to what? 13. I write the 3 down, and I carry the 1 up here. Now I have 1 plus 2, which is 5, and then I have 1. This is my answer. 1536. Okay, so some nice things about it. Again, it isolates so that it's a multiplication of single one digits. The other thing that it does, and actually the last method did this too, is it completely separated the multiplication step from the addition step. Because you see, our standard algorithm combines the two and we do it at the same time, doesn't it? We add in the middle of multiplying, and then we add in the end too. That can be really confusing when you change operations in the middle. It's the same reason that when I work with my daughter with flashcards on multiplication, I don't immediately work on her with addition cards next. It's going to be awful. Because she's going to be thinking multiplication because she's in the mode to do multiplication, and then getting her mind to switch to that addition in the middle of doing that is more challenging. So this one and the last two slides separate those steps out, and that is a nice feature. So any questions on these three algorithms? So again, let me reiterate, you don't have to like them, and it's okay if you don't. But what you need to do is you need to be able to have something else to be able to work with the kid on if they don't get the one you're showing them, whatever the one you're showing them looks like. Another option. All right. Next thing we're going to do is division algorithms. And there's just basically two division algorithms. One of them that you know and love, and the other one that you've probably not seen before. So the first one's called repeated subtraction. And we had a division model where we did a repeated subtraction process too. Do you remember the one where we were choosing teams, or I think my example was Abby's friends were choosing for rocks or something like that. And they all got one rock, how many rocks are left? They all get the second rock, how many rocks are left? It's the same idea here. All right, so we have the number 620, and we want to divide by the number 5. Okay, so repeated subtraction, what we're going to do is we're going to repeatedly subtract something. But I will wager that you do not want to repeatedly subtract the number 5 from this thing over and over and over again. It's going to take a while at the number 620, isn't it? So what do we do instead? Well, we kind of do an alteration of that. What we're going to do is we're going to subtract multiples of 5. And they're all going to say 5 and followed by zeros. Okay, so this is actually 5 times 100, right? So 5 times 100 is 500. 620 is big enough to subtract 500 from, so I'm going to subtract 500. And what do I get? 120. Now, I can't subtract 500 again, correct? But the next one I could subtract that starts with a 5 and ends with a 0 would be 50. And this is 5 times 10. Now, I understand I can subtract more, but I'm only subtracting the numbers times powers of 10. So whatever I'm working with over here, if it's a 7 or a 2 or a 5, like my 5 here, I'm multiplying that 5 by a number that's a power of 10, because it's the base of 10. Okay, so what's 120 minus 50? 70. And we ask ourselves the question, can I subtract that same 50 again? The answer is yeah, I can. And on the side, you're noting exactly how much you've subtracted every time. I subtracted another 5 times 10. This time I get the number 20. Okay, but I can't subtract 50 from that and still be in the whole numbers. So now I'm relegated to actually subtracting the 5s. Okay, so what's 20 minus 5? Okay, can I subtract another 5? Yes. And I get, can I subtract another 5? Yes. And I get, can I subtract another 5? Yes, and I get 0. And, oops, if we had gotten a remainder down here that said like 2, so that we could subtract another 5, we're just going to have a remainder of 2. That's okay. The answer then is actually along the side here. And actually, let me undo that. The answer is actually right here. It's how many times I subtracted something with a 5 in it. Well, I did it 124 times. The answer is 124. One of the things that this helps with is it helps with kids who do not have, not that I'm recommending your kids do not have this, who do not have their multiplication facts down very well. Because your standard algorithm that you know requires that you know your multiplication facts. And hopefully your kids will. But this does allow another option of how to think about division using subtraction. Because what happens on the next slide when we do our standard algorithm is that we have to know multiplication facts. In order to do this, I have to say, how many times will 5 go into 6? And you know it goes in once. So when I put the number 1 here, that is the number 100, isn't it? It is. So I'm actually subtracting off 100 times 5. Now, I know we don't usually write it as 500, right? You usually write it this way. And you bring this down and one more down, don't you? But by putting that 1 underneath the 5, it's 100 whether you write it there or not. Now when you look at 12, again, you have to know your multiplication facts. You have to know how many times can you multiply 5 and it still go into 12. And it's 2. And then you have to, again, know multiplication facts enough to say 2 times 5 is 10. But again, it's really not 10, it's really 100, right? That number's really 100, which was 50 plus 50 from the previous slide. I've got a result of 2 here, and I bring my 0 down. And I've got my 20 again. I have to know my multiplication facts to say how many times does 5 go into 20. 4. And 4 times 5 is 20. The remainder of 0, or whatever the remainder is left. So all your standard algorithm is a way of efficiently doing repeated subtraction. It really is. All right. What else do we have? Okay. I have a few problems in here that are going to be a little more applications based. So we have, I really should change the name because every time I come across this name, I don't know what it's called. What would you say? Juan? Even though it's a Z or an X? So Juan? Excellent. I love the way of pronouncing the X. We'll call him Juan. Juan saved $5,340 in 3 years. If he saved $95 per month the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So there's a lot going on. How would you start?
Do the first year first.
Okay.
Figure out how much.
So you want to start with the first year. All right, so Marilee, what would you do for the first year?
95 times 12.
Okay, and where did 12 come from?
Because it says per month and there are 12 months in it.
Right. Oops, I don't know where 92 came from. Let's try that again. All right, $95 per month, and there's 12 months in a year, so we've got 95 times 12. You can use 95 times 12 with all kinds of algorithms that you know, right? We've got 3 of them at your disposal. So I'm going to assume that you're going to use one of those 3 to do the problem, so we can continue through this particular problem. What would you get for that answer of 95 times 12? $140. Yeah. Okay. $11.40. So you're going to use one of those algorithms for multiplication, and you can use your standard algorithm as well. That's fine. But you're actually going to do the algorithm. You're not getting $11.40. Now what? Okay, so for the second and third year, we want to know how much we saved during those years. We can take $53.40 and subtract $11.40 from it, right? What's that give us? All right, 4,200, right? So this is what? What is 4,200? It's dollars. Dollars of what? What is it representing the problem? Yeah, how much you save in the second and the third year combined. Not quite what the question asked, but it was necessary to find. The question asked how much did he save per month during the last 2 years. So what we have to do next? Divide that by 12. So we would take, for our second and third month, we'll say monthly savings. It would be 4,200, and what would we divide 4,200 by? It would be 24, so where did 24 come from? 2 years, and 2 years is equivalent to 24 months, yeah. All right, so again, you can use your standard algorithm, or you can use an algorithm. This is a repeated subtraction algorithm. When you do this, which you will do the work for this in one shape, form, or another, what do you get? Dividing 4,200 by 24 right now. Yeah? Do you get an answer? Not yet. Okay. thing about the repeated subtraction on this particular problem is that you don't know a multiplication table for 24. So repeated subtraction actually starts to look pretty attractive at this point, because I don't have a 24's multiplication table to it.
So really anything over like 12 would be really helpful.
It would be, yeah. Most of it's about 12 multiplication. Did you get answers? No, it's okay, I just. You got 175, that is correct. So he would have to save $175 a month in the last 2 years for that to have happened. Per month. Any questions on this one? Okay, so that's combining 3 different things: multiplication, subtraction, and division, which is all 3 in the last 4 sections that we include this one. Let's try another one. This one's got a little bit of algebraic problem solving skills, essentially. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as in the third, and there are twice as many in the second box as in the first. How many does he have in each box? So how can we do this problem? Picture the boxes. So like this. So can we call this box 1? Box 2, and box 3. Now what?
Well, what I did, instead of labeling the boxes, I just, because the first statement says there are 3 times as many in the first box as the third, so I did 3x in the first box and put an x in the third.
Okay, so you started by putting an x in the third box like this.
Right.
And then you put a 3x in the first box. How come?
Because it says there are 3 times as many in the first as the
3
third.
times as many in the first. So 3 times whatever x is. Then what?
And then it says the second one, there's twice as many as the first, and it's 6x.
6x, and 6x came from
3x times 2.
3x times 2. So does everybody see where all the numbers came from first? Good, this is a good way to start. Now what? What do we want it to equal, Kinsey?
4,500.
Excellent. So if I add everything up on the left, what do we get? X equals 4,520, and then divide by 10. So what is x? 452. So let's make sure we answer the question, then we'll stop for today. The question says, how many does he have? It didn't say how much. How many does he have in each box? So x equals 452 does not answer the question, because there wasn't an x in the problem. So what would I do? All right, so let's start with box 1, box 2, box 3. What do you know? Box 3 is 452. Now what would you do? Multiply that by 3 or by 6 next, so let's do box 1 since it's first. If you take 452 times 3, what do you get? 1356. I'm trusting you. And then box 2? 2,712. And if we're lucky, no, if we've done it right, those will add up to the original 4,520, right? Very good.